Hello and welcome to lecture 14 of ECE 205. So in this lecture, we're going to kind of change topics a little bit and talk about the Laplace transform. So the goals of this lecture are basically for you to be able to know the definition of the Laplace transform, know a few theorems that can help us compute Laplace transforms, and to be able to compute Laplace transforms / to recognize when they don't exist. Okay, so rather than just jumping straight into the Laplace transform with kind of no motivation for it, let's give a little bit of background information here. Okay, so say if I have a differential equation, and for the purposes here, it really doesn't matter what equation I examine, but let's just say I have some differential equation, let me make that an x plus just some arbitrary thing here. Okay, so if I give you this thing, there's a different formulation that we can make from this differential equation. It's what's called the weak form of the differential equation. And to obtain it, we simply integrate everything. Okay, so from this thing here, one thing that I could do is simply integrate everything with respect to x. So if I do this, I'd get this new equation here where I start from some value x naught plus and go up to some value, say x up here, my y prime dx from x naught to x, plus this thing here, okay? Where here on the right-hand side, this would give me a constant because the integral of 0 would just be some constant, and that constant would depend on this initial condition, x naught. Okay, so given my original differential equation up here, I can turn this into a integral type equation. Okay, so one kind of easy, not really easy, but very good way to try to look for solutions to differential equations is to, instead of looking for differential functions that satisfy this, look for functions that satisfy this condition here. Okay, so in practice, instead of explicitly trying to find a weak form and solve the integral equation, what you can instead do is you can use what's called an integral transform. So just writing this out. In general, what an integral transform is this thing that you usually will denote with kind of curly font. So we'll do this with, I'll call this c, where c is going to be a function, but the integral transform of some function f of t. You could use x if you wanted, just depends here. This is simply going to be equal to the integral from some lower bound, say a, up to some upper bound, say infinity, of this c, which is just going to be a function that I'm given, of t multiplied by my f of t dt. Okay, and there I dropped the s that you have to have here. Okay, so, and then if we have one of these integral transforms, we simply can denote this thing by capital F sub c of s. Okay, so this is kind of the general formulation here. And the idea of this integral transform is that given any function c that I pick, I can define this thing, and if the integral exists and converges and all that good stuff, then I have this thing here. So why would I really care about integral transforms? Well, up here when I integrated everything, I actually took an integral transform of the differential equation and ended up with a different equation that I could potentially solve. So in this case, since I just flat out integrated everything, my c of s comma t would simply be 1. Okay? So in general, it turns out that if you pick good, where good is defined kind of more like useful, values of this c function here, then you can use these integral transforms in the kind of weak formulation of the differential equation multiplied by this kernel c of s comma t, can actually in some cases turn into, say, algebraic equations or simpler equations that we can pretty readily solve. This is the idea of the Laplace transform. Okay, so this is kind of the end of the background information section. This is why we ultimately care about Laplace transforms, but later in this course we'll talk about Fourier transforms, which are a different type of these integral transforms. So I just wanted to mention this now because, yeah, there's infinitely many of these transforms that are useful. Okay, so that aside, let's get into the actual lecture itself. Okay, so what is the Laplace transform? Well, we have this nice definition here. So definition 8.1.1. So I'm just going to post this here instead of just writing it all out here. Okay, so let f be some function defined for t greater than or equal to 0. Okay, so that's just some function I give you. And let s be a natural number. Okay, the Laplace transform little f is the function capital F defined by this integral here. Okay, so in terms of the nomenclature that I used before, this thing's going to be an integral transform, and this function here, this thing, is my c of t comma s. Okay, so I'll just erase that out there, but that's what that term is here. Okay, so why might I want to use this kernel for this integral transform? Well, if you recall, the solutions to at least these differential equations with constant coefficients usually have the forms of exponentials. Not always, but usually. So from that, it might motivate why I want to pick this type of form, but it just, in practice, it just turns out that this works for a lot of cases. So yeah, you could just use the if it works, we do it type of argument there. But nevertheless, this thing is not going to be necessarily defined for all functions f of t, right? Because this integral could diverge, in which case we say that there is no Laplace transform. Okay, so here a key idea is that we need this improper integral to converge. If it does not converge, we do not have a Laplace transform. We will discuss that later. Okay, so now let's look at an example of computing a Laplace transform just to get our feet a little bit wet and to see how this thing actually works and to show the things that you need to be kind of on the lookout for when approaching problems. Okay, so again, just steal an example from the book. Let's look at this example 8.1.1. Okay, so if I want to find the Laplace transform of this, what I really want to do, and you can use this is kind of one of the classic symbols for Laplace transform. Make sure you use curly brackets, but I really want to find the Laplace transform of 1. Okay, so how do I do this? Well, by definition, it's just going to be this thing, given that it converges. So we're not guaranteed that this will exist a priori. We'll get a theorem a bit later for existence, but for now, we just toss the stuff into here, and this is the integral I want to evaluate, if possible. Okay, so clearly this function f of t is defined for t greater than 0, and so this integrand is well defined. And now our goal is to simply evaluate this integral for all real numbers s. Okay, so it turns out that it's best to kind of split this up into some cases depending on what s is. Basically, evaluating this integral, we have slightly different approaches depending on what s is. So case 1, what if s is equal to 0? Okay, so in this case, what happens? Well, the integral from 0 to infinity would now just be of 1 dt. Okay, so now in this case, this would be equal to, and you could put it in quotes if you wanted, infinity, right? This thing will diverge. So in this case, we can say that the Laplace transform does not exist, or is infinity kind of your choice of nomenclature there? Okay, so now what next? Well, in the other case, we can kind of just start examining all of the integrals at once and simply evaluate this integral. So just to speed up this process, doing that would give us okay, so now this integral here either will converge or diverge depending on s. So from here we can split this up in two cases. So if s is positive, then this term goes to 0. So for the first case, we could simply say that this would be 1 over s if s is greater than 0. And in the other case, if s is less than 0, then this thing diverges, so we can say the Laplace transform does not exist or is infinite. Use does not exist, it's a bit nicer here. So if I put all of these together, then I can conclude that the Laplace transform of 1, so simply this term here, is simply going to be equal to 1 over s, and this is only defined where s is greater than 0. In the other cases, we get issues with convergence, therefore we can't define a Laplace transform. Okay, so a note from what's done in your text and what I'm going to allow you to do, instead of doing this stuff over here, where we are overly cautious, where we are overly cautious and do the limit as t goes to infinity of this, and then formally do the limit here, you can feel free to replace this t with an infinity and treat it kind of like it is a formal upper bound instead of rewriting this limit. The key thing is when you do that, you do need to recognize that it is a limit. So it is a good idea to write out the limits at some point, like here, to evaluate this. But just keep that in mind, that you can do that as a shortcut, kind of in the intermediary terms. And if things converge nicely for all values of s, you don't have to worry about limits. Otherwise, yeah, maybe throw in a limit just to make it a bit more clear of what's happening. Okay, so I'm going to do one more example of doing these computations just to show you how it's done. But I do recommend looking at the other examples that are in the text. I just have quite a bit of ground I want to cover, so I don't know if I'll be able to fit in that many examples in this lecture. If we can, I'll kind of go back later and then examine some more examples. Okay, so for this example, we want to find the Laplace transform of this thing where a is a constant. So here we don't know what a is, and thus we might is being the keyword there, need to break this up to different cases for a. But let's ignore that for now and just treat a as an arbitrary constant and see how far we can go. Okay, so in this case, the Laplace transform of this e to the at, by definition, this would simply be the integral from, say, some point, we'll just say 0. Well, actually, in our definition of the Laplace transform, it's always 0, up to infinity of what? Well, we have the kernel bit, so that's my e to the minus st multiplied by my e to the at dt. Okay, so from here, what we can now do is we can combine these together using exponent rules, and we get this. Which now, recognizing our previous work that we did over here, where we ended up just integrating this e to the minus st, if I pull out a negative, this functional form of the integrand is the same as what we had above. So let's pull out a negative here. Okay, so from here we can reuse our previous work, okay? So in general, if you were doing this from scratch, you would just use a u substitution to integrate this. Nothing fancy, pretty straightforward. But here, since we've already integrated this e to the negative st from 0 to infinity and found that it was 1 over s for s is greater than 0, we can simply reuse this fact here, okay? So from here we get this would simply be equal to 1 over the thing that was here, so s minus a, and this would be the transform whenever s minus a is greater than 0, or if you want to just kind of rewrite it, we get this. Okay, and we can do it here because a is something that's given to us. Okay, so now let's kind of consider cases where the functional form might break down. Well, hey, if a was 0, this thing becomes a constant, but if a is 0, this becomes 1 over s for s is greater than 0, which is exactly what we had for the Laplace transform of 1. Okay, so there's no edge case or anything like that going on with a, and we're all good here. Okay, and really what's happening is given a value of a, there's only some values of s that I can use such that this power here, this s minus a, is positive. And whenever this is positive, I have exponential decay at infinity, and therefore the integral converges and the Laplace transform would exist. Okay, so from here, I simply get that the Laplace transform of this, so if we highlight it up here, so this Laplace transform is simply equal to this with this exception here. Okay, so your text has those extra 2 examples, and I do highly recommend that you look at them. So I'll just put it out here real quick. And in practice, when just computing these Laplace transforms, at this point, all you have to do is evaluate those intervals, and don't do that last example there. Okay, now this can be quite tedious, and if we were stuck doing these integrals for every single time I wanted to use Laplace transform to try to help me solve a differential equation, which we'll see how to do that in a couple, 3 lectures. But if I had to do this process every single time, that's a lot of work. Luckily for us, there's a thing called a Laplace table, or Laplace tables. They're kind of like integral tables, but for Laplace transforms. So in practice, what you end up doing is, given some kind of functional form like this is the Laplace transform of blah, then all you have to do is kind of examine what you have, try to write it in the form of something in the Laplace transform, and then plug in and use the transform kind of as a rule, right? So let's look at a concrete example here, and I'll steal part of the solution because they tell you part of the transform that's in the appendix. Okay, so here we go. Use the Laplace transform to find the Laplace transform of this guy here. Okay, so here the table that's in the appendix, which just for completion, here is the table from your text. So yeah, given this function over here, this is what the Laplace transform is. These are kind of the common ones that you have here. And you don't need to memorize this, but it is a good idea to know kind of how to derive them. So if you want any good practice problems for Laplace transforms, try to derive any of these general rules. Some of them you want to use induction on and some tricks like that, but it's not too bad. But given this table of Laplace transforms, how do we go about actually finding a new Laplace transform? Well, here what we can do is we could compare the function that we want to take the Laplace transform of to one of the functions that the table has the Laplace transform for. So in this case, this is the element from the table that I want to use. Now note here, formally speaking, this should have a s is greater than a. Oftentimes, you'll just kind of notice that they drop extra conditions like this. I want you to be a bit more exact and can include the condition where you can, but generally speaking, it's kind of known from context what s needs to be, / sometimes you actually don't care what s is, because the goal is to use this transform to do some stuff and transform back. Nevertheless, in this case, if I just kind of look at these, I can notice, hey, n is 3, and hey, a is 4. So if I put this together, I can simply say that the Laplace transform of t cubed e to the 4t, this thing is simply going to be equal to, we'll just plug in 3 and 4. So 3 factorial, or 6, all divided by my s minus 4 to the 4th power. And this, again, is going to be for s is greater than 4. Okay, so the text doesn't put this extra little step here, but it is useful to know what the domain of s is. It's kind of obvious that s can't be 0, and if s is less than 0, bad things are going to happen in this case, but nevertheless, it's good to have. Okay, so in practice, in real-world problems, you're going to just look things up in the Laplace table. If I want you to do things with Laplace transforms, I'll probably give you a simple Laplace table, unless I want you to go through and find things via definition, which that's fair game to ask you a couple questions like that, or some questions like this. Okay, so the next natural question is, if I go up here, I started by talking about this differential equation and talking about its weak form very, very roughly, and talk about integral transforms. Well, if I want to take the integral transform of one side of a differential equation, it would be useful if I could split up these sums, okay? That would be a very useful property It's called linearity. We've seen it in linear algebra and places like that. So the natural question to ask is the Laplace transform linear? And the answer to this is, of course, yes, it is. All integral transforms are linear, which you could prove, but yeah. So let's talk about this theorem 8.1.2 and how this could help you. Well, in practice, say if I asked you to compute a linear the Laplace transform of something of this form here, if it wasn't linear, you couldn't split up those integrals, but because it is linear, you could split this up into the sum of these Laplace transforms. Okay, so if I asked you, for instance, the Laplace transform of this thing plus t, you just take this and you add to it the Laplace transform of t. Pretty straightforward. Okay, so the proof of this is very, very simple, so I'm not going to go through it, but the basic idea of the proof is you plug in the sum into the definition of the Laplace transform. You now have an integral. You can split up the sum because integrals are linear, and then since you can split up the sum, you then have it written as the sum of the Laplace transforms. Okay, pretty straightforward there. Okay, so natural question is, we have a new tool, linearity. How can we use it to try to find Laplace transforms? Well, the best way to kind of see how to use this to find a Laplace transform is to just get our hands dirty with an example here. Use this and a known Laplace transform to find cosh of b times t, where b is non-zero. Okay, so if I want to do this, the first thing I need to do is know what's cosh. Well, you might not know this, but it's kind of a common, well, it's the standard definition of cosh. So from here, cosh of b times t, this is simply going to be e to the bt plus e to the minus bt, all over 2. Okay, so if you remember from, say, linear algebra, when we defined sine and cosine using DMT, you could actually show that sines and cosines could be written as a sum or difference of complex exponentials divided by 2. So that's kind of where the naming scheme here for this cosh of bt comes from. Okay, so if I had an I in front of both of these terms, this is actually a definition of cosine. Okay, so that's just a little bit of the history behind cosh. It also is kind of the analog of cosine within a hyperbolic geometry, but you don't need to know that. Okay, so from here, this is the thing I want to compute the Laplace transform of. So basically, I don't have this or anything like this in my Laplace tables, but I do know how to do the Laplace transform of e to the ax. So just writing this out here. Like that. And from here, I now know how to compute the Laplace transforms of each one of these terms. So I could simplify this out as follows. And now here's where I need to be a little bit careful about the domains of each of these Laplace transforms. Because if the domains don't match up, then when I go to try to add these together, I could just end up with garbage that doesn't make any sense, right? So here I know from the table that this thing, the Laplace transform, is defined when my s minus b is greater than 0 or s is greater than b, okay? So that's where this thing is defined. Oops, I did not know I could erase like that. Okay, I did it twice. And then over here, this thing would be defined when s plus b is greater than 0 or s is greater than minus b. Okay, so these two things together, both of these restrictions need to hold for the sum, right? Because if I can't talk about s in one of the two terms of the sum, then the sum doesn't make any sense. So if you put these together, I get that this whole expression will be defined for s is going to be greater than b in absolute value, right? If s is greater than or equal to b in absolute value, then this is true and this would be true. Okay, so the next thing that we want to do kind of naturally is just to add these together, okay? So that's pretty straightforward algebra, so I'm going to skip the step here. But if you add these together by getting a common denominator, you would simply get that this would be s divided by this s squared minus b squared, which kind of makes this start to make a little bit more sense, where s is greater than b in absolute value. And again, the book sometimes is a bit relaxed when dealing with these domains here, but I want you to state your domains anytime you take a Laplace transform. Okay, so always make sure you state that. So the key things where you can get stuck here would be not reading things properly, standard algebra stuff, like doing algebraic manipulations to simplify this expression here to the one down here, or doing things with the domain. Okay, now that linearity is a thing, what's the next property that we could potentially have for Laplace transform? Well, it turns out that we have shifting theorems. So these shifting theorems are really powerful in the fact that they let you derive one Laplace transform from a different Laplace transform that you already worked with. Okay, so let's just state the first shifting theorem, briefly discuss the proof, and then look at some examples of the shifting theorem in action. Okay, so theorem 8.1.3 is this shifting theorem here. So if we have this Laplace transform for this function f of t for some s greater than s naught, then we can recover this Laplace transform f of s. Then we can recover the Laplace transform e to the alpha t times f of t by simply taking our previous Laplace transform and evaluating it s minus a. Okay, so why is this called a shifting theorem? Well, it's called a shifting theorem since all you're doing is really shifting the domain here. So why does this work? How does this work? Well, it's actually pretty simple when you think about it. So this top expression tells me that f of s is equal to this thing, right? So now here, if I just examine what f of s minus a is, I could simply compute this thing by replacing s with s minus a. So if I do this, this integral simply... Okay, and then here, if you actually look at this expression, this is my Laplace kernel. So this thing that I have sitting here is just going to be the thing I'm taking the Laplace transform of, and pretty much immediately we get that this f of s minus a is simply going to be the Laplace transform of this thing here. Okay, so what's happening with the stuff here? Well, the thing that I had for s was f of s was only defined for this, so now this new thing is going to be defined on, or I could say for, my s minus a is greater than s naught, which this is the same thing as s is greater than s naught plus a. Okay, so key idea here is if I multiply a function by this e to the at, all that does is shift the values of my s variable. Now, there are analogs of this shifting theorem that work if you replace this e to the minus st with a different function, but it does depend dramatically on what you use. Okay, so how does this help me? Well, this is actually probably one of the most powerful tools that we have so far for driving Laplace transforms from other stuff, right? So basically, from definition, we can build Laplace tables, right? That's what we did up here. We can use the definition to build these things. And now we have a list of things that we can use. A common thing we might want to do is take the Laplace transform of a linear combination of functions. And that's pretty easy to do if we have the Laplace transform of the individual functions that have taken the linear combination of down here. And now we have the shifting theorem, which gives me a way to get fundamentally different equations. Well, the Laplace transform of fundamentally different functions. Okay, so to give an example here, I'm going to go through part of example 8.1.7 in much more detail than they had there. Well, a little bit more detail. So find the Laplace transform of this thing, given the fact that we know what the Laplace transform of cos of omega t is. Okay, so if you looked at those previous examples that I mentioned for computing Laplace transforms by definition. One of those actually shows the work for computing the cosine, or you could just look into the Laplace transform. Okay, from the table. So from here we get cosine, the Laplace transform of it is simply this thing here. So if I want to use this to try to construct the new Laplace transform, this is how I would do it. Okay, so here, this extra little step where I use this nomenclature here, I really just did this so that you can kind of see the intermediary idea, is that you first evaluate the Laplace transform and then you do the substitution here. So it's probably best if I do something like draw an arrow, but you can use this nomenclature here if you are this symbolic form here if you really want to, but in practice you just plug things in. Okay, and then from here, if you wanted, you can simplify this one further just to make it a little bit nicer and rewrite it like this. Just to kind of have a more standard way of writing it here. Okay, so now, like I said before, this is probably one of the most powerful theorems that we have because it dramatically increases the scope of the Laplace transforms that we can compute. Basically, it doubles them, right? If I get the Laplace transform of some function, I can freely multiply it by an exponential, and I have that Laplace transform. So that's kind of super nice. And in practice, this is one of the properties that allow us to use Laplace transforms to solve the differential equations that we're going to be considering. So oftentimes, you've found things like this term here, where we took some function, say some solution to the homogeneous, or something that we want to be a unknown function from variation of parameters, and we multiplied it by a exponential term, right? Something like e to the minus st that solved the complementary equation, right? And using variation of parameters, we could find solutions previously, and this kind of looks like what we were doing there, but we're integrating it, so it's kind of like a weak form of a differential equation. So this is just foreshadowing what's going to happen in the lecture where we talk about section 8.3, where we apply these to solve differential equations, okay? Nice things are coming. Okay, so now we want to conclude by discussing the existence of a Laplace transform. Okay, so in general, we're integrating something, right? We're not always guaranteed to have an antiderivative for any value of s, so it is possible that a Laplace transform does not exist. Okay, so one example of a Laplace transform that doesn't exist is given in the text. Basically, if we try to take the Laplace transform of something like e to the t squared, this is where we run into issues, okay? So if we try to do this, this would be equal to this integral here. So 0 to infinity of my e to the minus st times my t squared. Oops. That. Okay, so from here, if I were to integrate this, I can try to add these things together. And I accidentally paused the video there. But once I do that, I would simply get this thing here. Okay, so now that I have something of this form, the question is, does this integral exist or not? Well, if I kind of take a look at this thing, this exponential term here, this t squared term, is simply going to be bigger than that minus st eventually, right? So I'm doing a hand-wavy argument here, but the basic idea is that t squared is greater than this st for some t bigger than here. For all t greater than or equal to some capital T for some t between 0 and infinity, okay? Basically, this t squared grows faster than st no matter what s is. What this is telling me is that in the limit, this term here goes to infinity, okay? Thus, from here, from this hand-wavy argument, we get that this thing diverges. So this is equal to infinity, or it diverges, or it doesn't exist, kind of your choice there. And this thing does not have a Laplace transform, no matter what s is, okay? So this is a problem. This means sometimes Laplace transforms might not exist for any value of s. We previously saw where it might not exist for some values. So how do we try to go in and quantify this a little bit? Okay, so the basic idea is this Laplace transform would exist if this integral could be bounded by some finite value for some value of s, right? So the natural question that we need to answer is, when does that happen? Okay, and to quantify that, we need to introduce this idea of piecewise continuous functions. Now, this will come back when we talk about Laplace transforms, so you'll see it then as well. So it's a good idea to memorize this definition. It comes up a lot in math. Okay, so what is a piecewise continuous function? So here's just the definition, and what I'm going to do is I'm going to draw some pictures to help you break down the idea of this definition. So a function f is said to be piecewise continuous on a finite closed interval from 0 to t. So let's stop here. Okay, so what I have for a graph is, say, here's my xy axes. Let's say this is my point 0, and let's say this is the point t. Actually, there we go. Let's start 0 at 0. Okay, so from here I have this closed interval. So now what I'm being told is that f0 plus, what is that? Well, if you recall, this thing is just the limit as x goes to 0 from the positive side of f of x. Okay, so from here we want this thing to be finite, and we want f of t minus to be finite. So again, just for completion, this f of t minus, this is the limit as x goes to t from the negative side of f of x. Okay, so really all this is saying is that I don't necessarily know what happens to the function at these points, and I'm just going to draw stuff in here, but I know that the function gets to some finite limit here, okay? It could do something fancy in the middle. It could oscillate. It could bounce around it as it approaches this thing, like with a decaying sinusoidal, like we saw in the cases of the damped harmonic oscillator, but it just goes to that point. Okay, so these things are finite, and f is continuous on this open interval, except for at finitely many points. This is the key idea, is this finitely many. So let's just highlight it as well, okay? So what is this really telling me? Well, here it's telling me that my function can kind of have some bad points. It could kind of maybe have a jump over here where it does something like this. It could have a hole with a little spot here. It could be something like this, right? So we can have different types of discontinuities here, but we can only have finitely many of these discontinuities, and they either have to be jump discontinuities, like this one here, or they have to be removable discontinuities, like this one here. Okay, so that is kind of the canonical picture of a piecewise continuous function, okay? I can have bad things happen, but only finitely many bad things. Okay, so what's the big deal with these piecewise continuous functions? Well, it turns out that piecewise continuous functions are integrable. We can integrate these functions that satisfy these two conditions on this finite domain, right? So an example of a non-piecewise continuous function, and cleaning it up a little bit there, but an example of a non-piecewise continuous function could be something like, say, 1 over x, okay? So this function is bad because the limit as x goes to 0 from the positive direction of 1 over x, this thing is infinity. It's not finite, so bad things happen, and you can't, in general, integrate this thing from, say, 0 to infinity. Okay, another non-example would be something like, say, 1 over x minus 1. So at this point, if I just look at this function, it's fine at 0, right? Because if I plug in 0, I'm down here at minus 1. Everything's nice and finite. It's continuous everywhere other than when x is equal to 1. So at x is equal to 1, what happens? Well, if I go from this side, as x gets closer and closer to 1, this thing, the bottom gets closer and closer to 0, remaining negative each time. So we get this going to negative infinity like that. And on the other side, we end up going to positive infinity. Okay, so this is continuous outside of finitely many points, right? But the kind of problem with what's happening on any closed interval, that includes 1, is this is a non-removable and non-jump discontinuity, right? It's an essential discontinuity. Okay, so this will be a non-example whenever I include 1 in that domain. And again, this isn't integrable because what do I do around here? Like, spoiler alert, there is a way you can do this for some things of this form called the Cauchy principal form. Not in this class, so we can't integrate it here. Okay, so now what is the second part telling me? So this is all about I, right, where I have this finite interval. Well, I is saying that, hey, I can define something to be piecewise continuous on an infinite interval if it's piecewise continuous on all of these intervals. So if I look down here at I, what this is really just saying is, hey, if you behave nicely here on any of these, say, finite intervals, let's just call this t1, for instance. So say if I have some type of nice function over here, it could have some, say, removable discontinuities like this, or just jump discontinuities. If it's nice here, and then it's nice on, say, this other one, t2, so we also do kind of nice things between there and there. And if this holds for all of the possible values of t that's greater than or equal to 0, then we'll say that this is piecewise continuous on the whole interval. So basically, since t could become arbitrarily large, it means it's nice for all of these intervals. So it means it's integrable on any finite interval. Okay? Doesn't necessarily mean that as t goes off to infinity, this thing will be bounded, because that's not true, right? Because e to the x would be an example of a piecewise continuous function. But it just means it's nice on all of these finite intervals. Okay, so the book gives a couple classic examples here of a piecewise continuous function, so I'm just going to include that just for completion. So if I throw this here, so here's just another example of one of these functions. Okay, so both of these would be piecewise continuous. This one over here is also continuous, so everything kind of fancy is happening. But here we have these jump discontinuities, finitely many of them, but that's not a problem for piecewise continuity. Okay, so again, piecewise continuity implies that my function will be integrable on any finite interval, but it doesn't say anything about that open set from 0 to infinity. Okay, so for instance, we can simply note that this function that we examined earlier, this e to the x squared, this thing is piecewise continuous. So it is piecewise continuous, a PC for that. And this is piecewise continuous on all of the real numbers, okay? So just writing that out in words rather than symbols. Okay, so introducing this piecewise continuity didn't actually fix this thing being a problem, since piecewise continuity really doesn't deal with boundedness at infinity or bad things that could happen at infinity. It just deals with all of the finite issues that we can run into. Okay, so how do we deal with these issues at infinity? Well, let's just go back and look at what that problem was with e to the x squared. So over here, the issue was that this exponential, this t squared minus st, eventually went to infinity no matter what the value of s was. And it turns out that this is precisely the other issue we must overcome to be able to have a Laplace transform. Okay, so on finite intervals, we had this issue here with the function might not be integrable if things kind of blow up in bad ways. And then at infinity, we have this issue where things can grow too quickly. So here we're going to introduce this idea of exponential order, or kind of asymptotics in general. And what is this really saying? So this is saying that a function is of exponential order, and in particular exponential order s naught, if there are constants m and t naught, such that f of t, an absolute value, will be bounded by this m e to the s naught t for t greater than or equal to t naught. Okay, so really what this is saying, the TLDR, is that f does not grow faster than some exponential. Okay, so just kind of for a quick example of showing you how to do this, I'm not really going to show you how, like, give you questions for how to do this, but just giving an example, let's just show that this thing is of this exponential order. Okay, so all I have to do is show, so we need to show that, well, I can find this m, I can find this s naught, which was really given to me. So from here, I just need to show that there exists some m in the real numbers such that, in our case, t, an absolute value, which doesn't matter so much here, is going to be less than or equal to m e to the s naught t, where t is going to be greater than or equal to t naught. Okay, and here the real thing that I actually care about is what happens at infinity. So let's just freely choose t naught to be t, right? T naught's a constant that I get to pick. Okay, so we could just freely pick t naught to be 0 because we think that that will work out nicely. And let's see what happens in this case. Well, the absolute value of t would be simply t, right? And I would want that to be less than or equal to m. My s naught was 1, so just e to the t. Okay, so here we picked this thing, so I'll say 4 over here, just for completion. So at this point, you kind of have the whole ream of calculus type things that you could do to show that this could be true for some values of m, but you could just note if m is equal to 1, then this thing is true. Holds. Okay, I'm not going to ask you to do these questions, so I'll be very lenient here, but if you kind of tie this together, thus you could say that in this case, we could let m be equal to 1, and we could let t naught be equal to 0, which here t naught doesn't matter so much, but we should probably be formal and throw it up here, so I will throw it here. Okay, so that's all there really is to showing that something is of exponential order, and the hard part again is doing this analysis of getting these bounds and showing that it's true. And like, for instance, to show this is true, you can't really solve for the zeros particularly easy because there are none. But in general, to prove it, you kind of want to use calculus tricks that are beyond the scope of the class a little bit. Okay, so that's basically what it means for something to be of exponential order, and that's how you could show that something is of exponential order. Okay, so now if f does not grow faster than some exponential of this form s naught t, then when I go to try to find its Fourier transform, I'll end up with, or sorry, not Fourier, Laplace transform, I'll end up with something here that's kind of this form, where this exponential will eventually go to 0 if I pick s to be sufficiently large. Okay, in particular, if s is bigger than s naught, then things will go to 0, just by definition of the definition here of exponential order. So exponential order is what fixes our problems at infinity for the existence of these Laplace transforms. In general, this is not something I'm going to super test you on a lot, but it is a way that you can determine whether or not a Laplace transform exists, which is important in practice. Okay, so I'm just going to throw out this theorem here. So if you combine these things together, piecewise continuity and exponential order, we can say if f is piecewise continuous on here and of exponential order s naught, then the Laplace transform will be defined for all s greater than s naught. Okay, so to prove this theorem actually takes a fair bit of work. Book doesn't prove it, I'm not going to prove it, but the basic idea is if this function f is growing smaller than e to the s naught, then things behave nicely at infinity for all values of s greater than s naught when I go to compute the Laplace transform. Okay, so do note this is sufficient but not necessary. What does this mean? This means that if this is true, then we can compute the Laplace transform, but it doesn't have to be true for us to be able to compute the Laplace transform. Okay, so basically there's some situations where things can oscillate in very appropriate ways to make that limit as you go off to infinity well defined, and those kind of edge cases are kind of problematic here. You don't really need to know that, but this is when Laplace transforms would exist. Okay, so now the book has quite a few examples that are pretty honestly good to go check out. They kind of tie into determining when something's of exponential order using basically asymptotics and a few little tricks like that. But I just want to point out one particular example here to kind of end things at. So find the Laplace transform of this piecewise continuous function. And here, basically, they go through the work. And let's just kind of talk about the main ideas here. Okay, so if I want to find the Laplace transform, I need to compute this integral. Okay, now since this is piecewise defined, when I go to compute this integral, I need to compute two separate integrals, one from 0 to 1 and one from 1 to infinity, and that's precisely because of this breakdown that I have over here. Okay, so one thing to keep in mind with things like this, given that I have something that's piecewise continuous, I can always turn this integral from 0 to infinity to a sum of finitely many integrals. Okay, so now what I need to do is I need to evaluate this integral here and this integral over here. Okay, this thing's pretty straightforward to compute. I can just do u substitution and I can find two different cases, one if s is 0 and one if s is non-zero. And again, the quantity between when s is 0 and non-zero happens because there's kind of the singularity in the functional form when s is 0. Okay, so next up, I need to evaluate this integral here. Okay, so the first thing I can do is I can note, hey, I can pull out the -3, and I can combine these exponentials to a single exponential of this form. Now, this is actually a Laplace transform that I can compute given one of those tables and the shifting formula. So it's kind of your choice of which way you want to go about doing it. But once the smoke clears, if you've done everything correctly, you will get this expression here. This expression down here, where s has to be greater than or equal to -1. Again, this term here comes from the fact that s minus 1, this term has to be greater than 0, which gives me this inequality here. Okay, so now what I can do is I can just put all of this information together. Okay, so in the case where s is not equal to 0 and s is greater than -1, both of these together, I get the sum of these two things is simply this term plus this term here. Thus, I get this branch when I put it all together. On the other hand, if s is 0, then this term is still defined and this integral is still defined. So I simply add them together and I get 1 from the factor here. And when s is 0, I get this term here when I just simply plug in s to be 0, which gives me that this exponent is simply 1, or -1, and this term here is simply 1. So if I put that together, I get this second branch here. Okay, so that's all there really is to Laplace transforms. The big thing I want you to get out of here is the definition, how to evaluate things via the definition, even when it's piecewise continuous type thing. Laplace tables, how to use them, the shifting form, how to use it, and just realizing that Laplace transforms might not always exist. In particular, they will fail to exist when the integral fails to exist. And one quantification that we can get for that is these two things here. If those hold, then it does work. It still could have a Laplace transform if the premise of this theorem doesn't hold, but it indicates that you need to do something a bit more fancy and ultimately go back to the original integral. Okay, so in the next lecture, we're going to expand by undoing everything we just did and talking about Laplace or inverse Laplace transforms. Okay, and finally, I want you to read section 8.1 for assigned reading, and there are some sample questions there. Okay, so for your meme, there's lots of things that we can do for Laplace transforms in terms of memes, but generally speaking, the good ones come after we actually start, after we get to section 8.3, where we can actually start using these a bit. But for now, yeah, don't forget derivatives and integrals. Do master Laplace transform.